Hey, I just started a video about a minute ago and it just quit on me. So um, I'll start this new one and quick catch up. So I'm going through the special right triangle stuff separate from Khan Academy. I looked at that more carefully this morning and saw that it wasn't really appropriate or overly helpful for what we're trying to do. I felt like it was making things a little more confusing. So we're going to ditch that and focus just on some basic things that I'm going to go through now. There are two kinds of special right triangles. One's a 45, 45, 90. One's a 30, 60, 90. These are special because they show up a lot. I mentioned in Canvas that they'll show up a lot in Algebra 2 and in pre-calculus and calculus for those that go on to that level. But they show up a lot even just in everyday shapes. This, if you took a square and drew in one diagonal, you would create two 45, 45, 90 right triangles. If you had an equilateral triangle, which show up a lot, this whole triangle here, 60, 60, 60, cut that in half, you have two 30, 60, 90 right triangles. Okay, so they do have value. They show up in regular hexagons, all kinds of places, and so they are emphasized as their own special things. But what we're going to do today is recognize that special right triangles, we can, well, let me just say it this way. If I had given you a number here, like 5, and you knew these angles, you would be able to use all the skills of trigonometry to say, find that hypotenuse, right? You guys could say, well, I'll focus on this angle, what we learned over the last couple weeks. This would be the opposite. This would be the hypotenuse. So we would say the sine of 45 equals 5 over x. And you would solve that. You guys have been doing that. Many of you have. Okay. And so that though gives you a decimal answer. All right. Special right triangles, we're going to understand how to get the exact answer. So this involves some of those radicals, some of those square roots, okay? And being exact is one benefit of this, what I'm teaching you. The other is being quick. So eventually you'll be able to do these and you'll know right away, oh, that answer is 5 square root of 2, done. Okay, I just have that memorized. I know the relationships, and so I don't have to do any of this, all right? Plus, it's exact, not rounded. Okay, so let's dive into how did I know that? How did I know that? Well, first off, with a 45, 45, 90, I think it would be fairly clear and obvious that it's an isosceles triangle because base angles are equal. That means the sides across from those angles are equal. So these two legs are always going to be the same. Very easy relationship. If I gave you a bigger one here, and I said this was a 45, 45, 90, and this was 16 square root of 7. I don't know, just pick a hard number. This one over here has to also be 16 square root of 7. Those legs are the same. Easy, okay? And then what you could do is you could go through the Pythagorean theorem, and I'll just do it for this one here. What would this be? Well, you could figure that out from the Pythagorean theorem. 5 squared plus 5 squared equals x squared. So you get 25 plus 25, 50 equals x squared, and then you're going to take the square root of both sides, and so you have the square root of 50 equals x. Now, we've talked about simplifying that a little bit. What two factors of 50, one of which is a perfect square? Well, that's 25, and it's 25 times 2 gives you 50. And so then the square root of 25 is 5, and square root of 2 is that. And so there it is. So that's what I had written down initially. 5 square root of 2 is your hypotenuse. Okay? And so notice the relationship. This is always going to simply be whatever the leg is times the square root of 2. Okay? So if I gave you this one, if I said this was 7, and then this would obviously be 7. What's this? Well, 7 square root of 2. That's it. Okay. What if it were, let's make it a little harder here. What if this were 6 square root of 3? Well, what would this other side over here, this other leg would be 6 square root 3. And this hypotenuse would just be, all I have to do is take it times square root of 2. Well, what is 6 square root of 3 times square root of 2? Well, I can take square root of 3 times square root of 2 to get square root of 6, so 6 square root of 6. Okay. Now, what if I went the other way? What if, I keep losing my stuff, guys, sorry. What if I gave you the hypotenuse of a 45, 45, 90? What if I told you this here was 8 square root of 2? Well, you guys could probably figure out, because we multiplied by square root of 2 to go this way. If we want to go back the other way, we're going to do the inverse of multiplying, and we're going to divide by square root of 2. So 8 over square root of 2 divided by square root of 2. Those just cancel out, leaving you with 8 and 8. Okay. What if it were a little harder? What if this were 10? What would these sides be? Well, again, if we go backwards, we're just going to divide by square root of 2. So 10 over square root of 2 is that value. But we know that would be easier, or I should say that we should rationalize that by multiplying by square root of 2 over square root of 2. So 10 square root of 2 over 2, and then 2 goes into 10 5 times, so 5 square root 2. 5 square root 2. Okay. All right, so that's a quick introduction to the 45, 45, 90s. I'll maybe make a separate video for the 30, 60, 90s. But you can start with that and see if that gets you going okay on those. Thanks, guys.